Welcome back, everyone. In the last video, we were talking about correlation. And in this video, we're going to talk about a related concept called regression. Now, if you recall from the previous video, when we're talking about a correlation between two continuous variables, we're trying to measure the association between these two continuous variables. But in a correlation, there is no clear predictor and clear response. Positive correlations simply mean that larger than average values of one variable are associated with larger than average values of the other variable. And in this way, correlations then range between -1 and 1, where a correlation coefficient of -1 means that the two variables are perfectly negatively correlated, and a correlation coefficient of +1 means that the two variables are perfectly positively correlated. But in a correlation, there is no obvious predictor and response variable. Whereas in regression, there is a clear predictor and response variable. In a regression, we're interested in trying to predict values of one numeric variable, that is our response variable or our y variable, and we want to predict those values from values of another numeric variable called our predictor variable. So in a regression, we want to predict y from values of x. And we do this in part by assuming that the relationship between x and y can be described by a straight line. And so that's what we mean when we say a linear regression. So what is the difference then between correlation and regression? Well, if you look at these two plots on the left, they have the exact same regression slope, meaning the slope of both of these relationships is equal to 0.8. But the plot on the left has a much higher correlation than the plot on the right. That is, there's a perfect correlation. The dots all fall right along the straight line in the plot on the left, and the correlation is lower on the right. In contrast, these last two plots have the same correlation coefficient of 0.6, but very different regression slopes. This plot here has a regression slope of 0.8, and this one has a regression slope of 2. So correlation and regression are similar, but they're not the same. Now, just like any of our statistical measurements that we've talked about so far, we represent parameters from the true population using Greek letters and estimates from our sample using Latin letters. So in the case of a linear regression, we represent the intercept and slope from the population using alpha and beta. So what these represent are the true intercept and slopes associated with the relationship between our predictor variable and our response variable in the population. And we estimate alpha and beta using a sample collected from our population. And when we perform our linear regression then based on our sample, what we estimate are A and B for the intercept and slope, respectively. So our slope then represents the rate of change of y for a given change in x. So the slope can be positive, where for a given increase in x, y also increases. The slope can be negative, or there can be no relationship at all between x and y. In contrast, the intercept just determines where the line crosses the y-axis. That is, the intercept is defined to be the value of y when x is equal to 0. Another way to think of it is that the intercept represents the height of the line. So in the far right plot, the solid dots have a higher intercept than the open dots. Now, when we perform a regression, we assume that our observations come from a random independent sample and that y is normally distributed with equal variance for all values of x. But unlike our correlation, our regression actually makes no assumptions about the distribution of values of x. So when we perform a regression then, we assume that at each value of x, there is a population of y values whose mean lies on the true regression line. And this is what we mean by our linear assumption. And so notice that we're assuming that there is some uncertainty in y, some variability in y at a given value of x. But we have not assumed uncertainty in x. In fact, regression assumes that x is measured without error or is known with certainty. So then how do we go about calculating what our estimates of A and B are in our linear regression? Well, for this, let's walk through an example where researchers in Tanzania were interested in estimating the relationship between a male lion's age and the proportion of its nose that's black. And if the researchers could perform such a relationship, it would provide them with a way to reasonably age lions from photographs of the coloration of the lions' noses. So here we have plotted the relationship between the age of the lion on the y-axis and the proportion of the lion's nose that was black along the x-axis. And so here we've got age on the y-axis because we want to try and predict age from an observation of how black the lion's nose is. And we can see that overall, males that are older have noses that tend to be more black than males that are younger. So how can we go about performing a linear regression with these observations? Well, you can imagine that we could fit any number of different lines to these data. So we might draw a line that looks like this. We might draw a line that looks like that. We might draw a steeper line. Maybe we might draw a really steep line, or maybe a line that is straight across. So how can we judge how appropriate each of these lines is for the data? Well, one of the ways that we can do this is by measuring how different each observation is from the line. And these are what are called deviations, or in the case of linear regression, called residuals. And so we can see that if we draw a line that looks like this and calculate how far away each observation is from the line, we can see that the line and the dots are pretty far away from one another on average. Now here, if we take the line and instead of making it negative, we make it slightly positive, we now have smaller deviations between each observation in the line. And if we make the line steeper still, now we have even smaller deviations between each observation and that fitted line. So we can talk about these deviations between our observed values and the line a little bit more specifically in this example. So our observed values, our observed relationship between x and y is shown by these black dots. These are our observations. And we fit a regression line to those observations. And what the fitted values are simply the value of y along this line corresponding to the x value for each observed observation. And so we can calculate then the difference between the observed value of y and the fitted value of y for each observation along the x-axis, where the deviation between the observed value and the fitted value is referred to as the residual. So for each observation I, we have some observed value and some fitted value, where the difference between the two of them is called the residual. Now, when we perform a regression, Some of the observations will fall above the line and have positive residuals, and some of the observations will fall below the line and have negative residuals. So we can calculate the regression line that best fits the data as the regression line that minimizes the sum of squared deviations of observed values from the fitted values. So when we perform a regression, we're trying to minimize these sum of squared deviations between our observed value of y and the fitted value of y across all of our n observations. And so when we do this, we would find that our calculated slope from our line of best fit is equal to the covariance between x and y divided by the sample variance of x. So if you recall, this is slightly different than our calculation of our correlation coefficient, which was equal to the covariance between x and y divided by the square root of the product between the variance in x and the variance in y. So in this case, the slope is equal to the covariance between x and y divided by the variance in x. Anytime we perform a regression, the regression line always passes through the mean value of x and the mean value of y. And as a result of this, once we've calculated our slope from our covariance and our variance, then we can simply calculate the intercept as being equal to the mean value of y minus the slope times the mean value of x. And so when we do this for our line example, this is the line of best fit that we get, the line that minimizes the sum of squared deviations between each observed value and the fitted value. So this is our linear regression. This is our line of best fit. So a regression then represents a method used to predict some continuous measure from values of some other continuous measure. A regression is different from a correlation because in a regression, there is a clear predictor, x, and a clear response, y. So we're really asking then, what is the effect of x on y? And we estimate the slope in our regression by minimizing the sum of squared deviations between each observed value of y and its fitted value along the line. And this is what we mean by creating a line of best fit, the line that best fits the data, and the measurement that we use as a measurement of fit is the sum of squared deviations between each observed value and the fitted value.